Hey dudes, we're checking out 7.4 area under the curve. It's out of 19A and B from the text, and we're in a little bit of a different place, but that's all right. We can press on anyway. So here we go. Area under the curve, we've been working with, you take your function and you integrate, use the definite integral between 2 points, and it gives you the area under the curve, right? That's not a big deal. So the A, we've already kind of worked with A. One way you can look at that is if you're looking at y equals 2x, this was your function, you could find the area by saying 1/2 base times height and using a geometric argument, right? 1/2 base times height, the base is 4, the height is 8. So, we're integrating between 0 and 4, right? Get your head out of the way, G. And then, so this is being what, 16? Great. We can also do it by integration, which I'm sure you're comfortable with by now, integrating between 0 and 4, integrating 2x dx, right? Integrating that function. When we do that, it turns into x squared, and we integrate between 0 and 4, which means we substitute in 4 and subtract when we substitute in 0, right? And we still get 16, just like we expected. So kind of overkill with calculus, but that's all right. So that's part A. Part B is the area between two functions, which works like this. If this is our function f of x, right? The area underneath is f of x. It's the integral. Ooh, too much. So that's this area, yeah. And if we had some other function g of x, small g, the area underneath is, so that's this piece. So if you wanted the area between the two, this red area, this would take f of x and subtract g of x, right? You take this away and you'd be left with this red part. Yeah. So that's the area between the curves, is the area of the larger part minus the area of the smaller part. Upper bound minus lower bound, sometimes you see. So you're just subtracting, right? So this is sort of the formal definition of it. If you look at the area of two curves, you pick the upper bound is f of x, so let's call it this. The area under the curve is all of this, right? And the lower bound is g of x, that's this guy. And the area under the curve, the integral, is all of this. And if you subtract the two, if you go green minus blue, you end up with just the piece you're looking for, which is this red component. Yeah. And it doesn't really matter if sum is below the x-axis, sum is above the x-axis. If you added some c term to both of these, if you added, or k, let's call it a k term to both of the equations, it would drag this whole piece up. You could make it high enough so none of it's below the x-axis, none of the area, and you'd have the same integral. So it really doesn't matter where it is. All right, so let's try it out. We want to find the area of this region enclosed by a linear and a quadratic. You don't have to graph it all the time, but here's the visual of it. Here's the linear, here's the quadratic. We want to find the area between the two, and so first of all we need to find like these spots, and it's nice that they're here on the graph, but I need to know when to start integrating and when to stop integrating. And so we can do that by setting, I know at these points both the x and y for this function and this function are equal, so we can set these two equal to each other, right? They meet when one equals the other. We put everything to one side, put all the x's and y's to one side, missing one, and solve this way, so plus and minus 2, just like we expect from here. Great. So we're going to integrate between negative and positive 2. So the area of this is the upper boundary, the region bounded by the upper layer minus the region bounded by the lower part. So it looks to me like the part. So that's this piece, and the quadratic is the lower boundary, so that's this piece, yeah? So you can just throw those in there, right? And you can either integrate each piece, or you can put them together and then integrate that, and that's usually a little easier if you're subtracting. So when you subtract, be careful to distribute the negative and clean it up a little bit. It'll look like that, and then we can integrate. right? When you integrate the 4, you get 4x. When you integrate the x squared, you get 1/3 x cubed. And then we integrate from 2 to -2, which means we first plug in 2 into there, and that's this component, right? And then we plug in -2 into there and there. All right, and then when we evaluate from there, we get this results and we can subtract them, and this ends up with 10 2/3 as our total area under the curve. Nice. All right, let's move on and try one more. We want to find the total area of the region bounded by the x-axis and this function. And if you thought about that in graphical form, it would look like this. The first area that we want to attack is trying to find these locations between which we want to integrate. And you find that by solving this, setting this equal to 0 and solving. So you say, all right, well, when does this equal 0? You can factor again. And so if you didn't have the graph, you could find -3 from here and 0 from this and +1 from that. Those are our locations between which we're going to integrate. So when we integrate, you can just take each piece and say, all right, well, all of this is this integral, right? This area is the integral of the function between -3 and 0 from here to here. And this is this piece. It's the integral from 0 to 1. And when we integrate, you integrate each piece just like you would normally. So x to the 4th over 4, etc., etc. For each piece that should be the same because it's the same function. And then you substitute in your values for 0 to 3, right? The top minus the bottom. So that put in the 0 first, and then subtract from the 3. So that's where this comes from. And then you're subtracting the area under the curve here, and you do the same sort of thing. You drop in the 1 first, and then you drop in the 0. And you should end up with this, 11 5/6. You can do this with your tech if you're interested. Plug in, my emulator's not on this computer, but you can plug in that function, same thing, right? Ask it to graph. Oh, don't look. Ask it to graph, and goes like that for you, right? No surprises. And then we can ask it to calculate, right? So say second calc, and you can ask it for an interval, right? So go down to 7, hit enter, and it says lower limit. Where do you want to integrate from? Well, we want to integrate from -3. So plug in -3. It says upper limit. Well, we want to integrate all the way up to 1. Yeah, so what about 1? And it gives you that and that. And it gives me 10.6, which is not what we expected here, right? So the calculator's adding the two pieces together, but it's integrating this top portion and subtracting that bottom portion, right? If you want them to combine them, right? If you want them to actually like add the two up, you have to have a positive area here and a positive area there, and so you're going to use the modulus function. Modulus, its absolute value, right? You find that with math, so you'd have to reinsert all of this. You'd have to say insert in math over in number. There's the absolute value. Modulus just means distance from 0. Right? I'm going to add that to there, and then I'm going to close some parentheses, and when we regraph it, boing, 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 we only get the top half of this graph. This is the same graph, right? I'm just pulling this over here so you can see it. Right? This is still positive, but the modulus makes this piece pop up to here, and it flips this piece over. Right? So now if you say, calculate the 7, from lower limit we want to go from -3, upper limit we want to go to 1, please calculate for me, and now it finds all the positive stuff. It has to think a little harder because it's using a modulus function. Cool, and now it says 11.8, which is what we were expecting back here. Oh, where'd all my stuff go? Right, 11 and a little bit. Cool. So how do you know which to use? Well, it's all about context. So here's some context. We figured out, this is a velocity and time graph, and we figured out in one of our first sessions that if you're looking at velocity, meters per second, and multiplying by time, the seconds cancel and you're left with just a distance value, right? It's because velocity times time is distance. So the area under a velocity time curve tells you how far a particle has gone, or a car, or whatever. So if this is the velocity of an object in time, what's happening with this is it's starting from zero. It's starting from zero, and it's moving here, the area under here, it's moving in a positive direction. You can tell because the velocity is positive here, right? It goes up, it stays constant, and then it comes back down. And at this point, it stops. So the particle's moving forward, and then it stops, right? And then it has negative velocity here, and the area under the distance it's traveled, it stopped. It has negative velocity. It's moving backwards, right? And the area is this distance, right? So this area is this distance, is this distance. So if you add them and keep the negative and positive signs, it tells you how far the object has been displaced, as far as it moved from the original location. Right, so then take into account the negative. On the other hand, if you wanted to know how far has it moved in total, right? I don't care where it is right now. I just want to know how exhausted is this little particle from moving so much. You could think about the modulus function, right? This is still the distance it's traveled going forward. This is the distance it's traveled going backward, right? But if you don't care about the direction, then don't worry about the sign. Just combine the two areas. So here's positive area and positive area, and it's essentially like flipping this over and saying, okay, well, I'm adding the two together, and that will tell me how far to go in total. Oh, I turned it purple. So if you add this and this, it gives you total distance traveled, right? Just some context. Sometimes it's difficult to know. An easy thing to do is, instead of, if you're working with your calculator, instead of if you're not sure, instead of finding the integral across the whole distance, find just the pieces you want and then think your way through, do I add or subtract based on context. Yeah? Great. One last piece. You can't integrate with these same tricks if there are holes or jumps or asymptotes in the function. So when you see an asymptote, and you shouldn't very often, you might have to think about how to break it up and think about the area under here, because this asymptote wreaks havoc with our integration. It's not that it can't be done, it's just that other considerations need to be taken, and that's not where we are interested in going right now. So, glad you made it, good to see you, and I'll catch you next time.